Okay, so welcome to the final guild meeting. Today we're going to implement the latent diffusion model that we talked about last session. And Airtable, let's go straight to the Colab notebook. Today's coding heavy. I'm gonna leave it up for you. And we're just gonna implement that diffusion model and see like the results that we can get with it. You there? Okay. Yeah, so I'm just gonna kind of walk through the design of the system first before we kind of code it up. You see an example right here anyways, but we have, for example, we start in the image space. We talked about this last time. Remember, the whole philosophy of diffusion is we have our forward process where we add a little bit of noise each step, all the way till we go straight into like pure Gaussian noise. And we have to, in our forward step, we kind of just pick like a time t to start in. And from there, we start reversing or teaching a model to learn to reverse that noise step. So then the other side of things would just be this reversal. When you do inference and generate an image from scratch, you start from the Gaussian noise, you go straight to some image. And the model that you taught slowly removes that noise. The way this model works, do you remember kind of like the step-by-step process or the big players in
is it like the kind of like the hills?
The hills, yeah.
Yeah, it's like it.
And then the main architecture we're using, the unit, right? Like
Yeah.
So what's it called?
Oh, like, did you send out the link already to the?
Yeah. To the notebook.
Okay.
Copy it and then let me know. But in this instance, we're going from without increasing complexity, right? This is just, I tried this for efficiency purposes. We're going to use a variational autoencoder to go from the pixel space to the latent space. But ignore that part. For the most part, the diffusion process inside the latent space is the same. So the way our model works, we have the pixel space. That's where you actually have the image, right? And then you encode that into the latent space. So then we have some representation of it. And from here, we just do the same thing. We add noise to this representation over time. And then the main part of this diffusion process is the unit. Remember, we have the U. We have each layer kind of two convolution layers downpool, convolution layers downpool until you have the bottleneck. And then you go right back up with the skip connections that we add at every step. And remember, this is our main architecture. We're going to spend most of the time designing this so that when we go backwards, we have something that generates our representation of the image, pass it through a decoder, and then we have our representation of the house, maybe like with something extra. This part, we call it the latent space. And then remember, we talked about the text, how we're going to use prompts. You can kind of imagine like the text portion of things. This is like the clip model. Whatever our text is gets transformed to some text embedding. And then we're going to literally inject the text embedding using cross attention at each step of the unit. So from here, like you can kind of imagine the text embedding kind of going through each layer of the unit. And this guides the unit towards fitting and generating an image that's similar to our text embedding. That's kind of the process that we're going to work on today. I'm going to try to connect to an H100 so that inference can be faster. Dude, I spent all night training this model. And it's heavy on the computing side. You're going to need a lot of time to train, like over 15 hours to train. So don't worry if you don't like obviously we're not going to train the model here now. But also don't worry about like the data set or anything. Just try to get the logic of the code through first, and then from there we'll see the level of generation that we get. Yeah, but yeah, pretty much. Well, it's possible that the H100s aren't even available right now, so don't worry about that. And we're gonna just run these first couple cells. Here I'm just installing the dependencies and the libraries that we're gonna be using, mounting your Google Drive, and importing everything that we're gonna use throughout the training process and everything. Again, the training part, you could do it yourself if you want. If not, it's okay. Like that training part isn't the important part. The important bit is understanding the architecture behind it, the intuition behind why we're doing what we're doing, and you're set from there. So you see, I wasn't even granted access to the H100. So I gotta restart my runtime. Next best thing you could do is connect to an A100 GPU. Okay. So yeah, while that loads, I'm gonna just install everything. And for the data, for the environmental setup, yeah. For the setup of the environment, you have two options here. Pick whichever one you want. Again, it doesn't really matter. We're focusing more on the code, not the data set itself. We're going to be using the same MS Coco data set that we used for our clip implementation. So I'm going to just move on from this part right here, and we're just going to go straight to talking about the data set. This is our data set. Again, MS Coco, we've used it like 3 times before at this point. And this is just running the cells and pre-processing the data set. Here we normalize the images. Probably the most important bit of that pre-processing step. And yeah, here is our variational autoencoder. This is what changes it from the pixel space to the latent space. Don't worry about that part, but here is also where we import clip. And if you remember, we've done a clip implementation in PyTorch. You could go to the repo here. I think it is very, now looking back at it, it's a very simple implementation compared to a project of this scale. And yeah, I think I'll load it just so that I can do the inference and so that we can kind of look at the progress, but you don't have to load it yourself. And we have the VAE here. Again, don't worry too much about this part. This is just another layer of complexity. Just think of it about it going from the pixel space to the latent space. And these are some helper methods that we have. I have get text embeddings, where given a prompt of an image from our data set, we just get the text embeddings using clip. And then these are the encode and decode to latent and to pixel space back and forth. All right, this is the fun part and the complex part. This is our diffusion area. So for diffusion, you remember all the crazy math, right? These are the important formulas that we have. I kind of wrote them down here. We're literally going to code these formulas and kind of see the adding noise process, so the forward, and the removing the noise, so the reverse. And it's literally an implementation of these formulas where we add Gaussian noise using a closed form equation and generate it backwards in this reverse process. And yeah, that's what we call our scheduler in the code. So starting off in the scheduler, we want to, well, you see our inputs, right? We're just going to define our inputs. So self dot, the number of time steps equals the number of time steps. And now the variance schedule. We're going to be using a linear variance schedule, and we'll probably get more into that today as I go on. But we're just going to define our betas in just this sequential line space of starting at beta start ending at beta end, and we do that for n number of time steps, which we'll implement here. And I'll annotate the code as we go along, right? This is just a linear variance schedule. You can kind of see what's going on here. So for each number of time steps, we go from this start to this end. It's not anything too complicated. That's our betas. And remember what our alpha is. If we go up here, our alpha t is equal to 1 minus beta t. So you can kind of think of it as if beta is what we're taking away from the image in terms of noise, the alpha is what we're keeping in the image. So I'm drawing. Yeah, so should be good. And then for the alphas, it's well, we talked about it right now. So self.alphas equals 1 minus our betas. So original, you kind of think about it as the original signal that we keep per step that we take. Right now it's pure mathematics, straight up. And remember, in the code at one point we had to make the alpha bar. This is just the cumulative product of alpha. So we define that here, right? We define an alpha bar is equal to the cumulative production of self.alphas given our axis equal to 0. And in this part, after this alpha bar part, we're gonna just define a bunch of the little variables that we're working with. We're on this step right here. And we're gonna define all these little variables just to have them as individual variables in code so that it's not too complex to calculate. We're going to make self.alpha bar previous. So the previous alpha bar value. Here we're going to concatenate self.alpha bar. So we're picking basically the previous alpha bar. And for the next variable we're going to define the square root of the alpha bar. And it's straight up just JAX numpy square root of alpha bar. Same thing with this bit right here. This 1 minus alpha bar square root. I'm also going to define it as its own variable. So just to name it, it would be the square root of 1 minus alpha bar. Same thing right there. So it's just 1 minus alpha bar put in a square root. And then the reciprocal of that. So right now, it's not anything too complex logically. It is just copying variables and kind of creating our environment to perform like all this crazy mathematics and stuff. So we already have the reciprocal of alpha, right? Yeah, so these are the variables we're going to be working with. And now let's go to the forward process. This is where we add noise, right? And we're just going to define the square root of alpha bar at this step, right? Square root alpha bar is equal to self dot square root alpha bar, right? At a specific time step. So that picks a pre-calculated scaling factor. And same thing with the 1 minus, right? The names are a little tedious to write out, so don't worry about that. So square root of 1 minus alpha bar. Let me put the minus, I forgot. Is equivalent to the same thing, self dot square root 1 minus alpha bar at time steps. So in this forward process, we're literally, dude, you're gonna see it's literally this equation. We're just coding this equation out, since this is what tells us exactly what a time or what amount of noise is at a specific time step B. One little caveat, we are broadcasting just a batch to this 4-dimensional vector, because square root of alpha bar is just like 1D variable. So what we're gonna do is square root of alpha bar, and I'd like to do this using INSUM. So you should have it imported. It shouldn't give you any errors. If not, it's okay. We'll go back and look at that part specifically. So we're going to rearrange. And if you remember this, this notation, right? We have the square root of alpha bar. And then what we're going to do is literally this. We know that it's size batch right now. And what we're going to do is change it, rearrange it to a size of batch, and then 3 different dimensions of size 1. This is so that we can do computations with the images, because images are 4-dimensional. There is the batch dimension, height, width, and color dimension. I have to say one thing. I know we've been working primarily with PyTorch throughout the semester, but in JAX, it is this orientation instead of in PyTorch. You know how the channel goes in the third or in the first index. So that's something to keep in mind as we like take care of the shapes throughout. All right. And now we literally do the same thing with 1 minus alpha bar. This is just some tedious mathy stuff. And right here, now that we have that, this is literally our implementation of this. All we do is x of t. Here, x of t, right? Let's look at the formula real quick. So it's x of t is equal to the square root of alpha bar times x0 plus the square root of 1 minus alpha bar times an epsilon. And literally that's what we're going to implement right here. So it is not too complex, right? We have square root of alpha bar times x at time step 0 plus the square root of 1 minus alpha bar times noise. And that's what we're going to return. It's literally that simple. The noise is this epsilon. The epsilon is this noise right here that we just randomly sample from a normal distribution. So that's that. That's literally the forward step. So we went from at this point, for a random time step, we went from a clear image to some fuzzy, noisy image. And then what we do in the reverse part is, or in the step part, is literally the reverse process, right? So I defined the alpha and our variables at a specific time t, and now do the prediction of this. Oh shoot! Let me give you guys access to. I think everyone's here. Yeah. Let me give you guys access to the notebook. That's the URL. Kind of just follow along the code. Don't worry about actually running the cells too much. It's very heavy computationally. Give that a little bit of time. Okay. Let me know if you guys need the link still, but I'm gonna go back to the code. This is kind of what we've done. We've built the scheduler. It's literally just this math. And if you guys need also, the final copy is down here. I always put the final version down here, so don't worry about that too much. Just follow along from this step here. Where are we? Yeah. So now we do the reverse process. We already defined the variables. And for the prediction, we're going to define a coefficient, which is beta divided by the way, what we're doing here is this part. This is the coefficient. Beta. Yeah, I got you. Okay. We're defining this bit right here, literally that part. So it's beta. We already have our beta, and we are going to divide it by the square root of 1 minus alpha bar. Literally this part right here. Beta divided by 1 over the square root of 1 over 1 minus alpha bar. And then we just define our mean. So this is this part right here. We kind of just do this whole computation. Again, it's nothing too complicated. It's just copy and pasting or translating mathematics into code. And here we have our thing, right? So 1 over the square root of alpha times x at time t minus the coefficient times the noise that we predict. Remember, here we're going in reverse. So you could think of this as taking noise out of the image. And then we calculate the distribution. We return a variance as well. But literally right here was just this math. X minus coefficient, right? X minus coefficient times the noise multiplied by 1 over square root of alpha. Same thing. No complexity at all, no hidden logic. It's literally the same thing. And from there, now we're going to go to the fun part, the unit. I'll do this one in blue. If I have any space, I'll do it right here. You see the unit there. I don't think I have to draw anything really, but let's think about what the unit architecture is showing us. This is literally like building Legos. We have like imagine this is the individual blocks, right? 1, 2, here they have 2, 3, then they have the bottleneck right here. Let's just focus on the encoder part. This is the 64 part. You can see there's 2 convolutions, 2 convolutions, 2 convolutions, 2 convolutions, and then a max pooling layer at each side. And remember that in the unit, at each layer, actually, in this implementation, I didn't do cross attention in the first layer, but for the rest, yes. In each layer, we're literally going to inject some context by the way of cross attention, my bad, cross attention, cross attention, cross attention. And you're going to see the cross attention code. It's literally the same thing as what we did in the GPT-2 implementation, just with some reshaping due to the image sizes. But we'll get to that then. Here we're just building a ResNet encoder. The upscaling part might be a little weird. And then remember the skip connections. Whenever we take a step down, we have to save whatever our output is here, 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 so that later we can skip it to the other side whenever we encode. And you're going to see that's literally what we build. But the first thing, each layer has 2 convolutional networks or 2 convolutional layers, and that's exactly what we're going to code up. So we're going to start off. Don't worry about this time embedding. This basically is telling our neural network to learn that logically at time step, we talked about this before, right? At time step 500, there's obviously going to be a lot more noise than at time step 2. And so the model has to kind of learn like, okay, if I'm in time step 500, I have to take away a lot of noise, or I have to focus on a lot of noise. If I'm at time step 2, I shouldn't be taking away a lot of pixel strength, intensity, whatever, because I'm at time step 2, so there shouldn't logically be much noise in that image. That's basically our time step embedding. So we embed it, and then you see here we have a time multi-layer perceptron. At that layer, it just basically learns that encoding. High time step, lots of noise, low time step, not too much noise. So we define our first convolutional layer, or convolutional layer. In JAX notation, it's like this. What do? We put the input is the in channels, the output is the out channels. And then we do this with a kernel size of a 3x3 kernel, literally exactly what it's telling us here. So we're more or less just copying through what the architecture is showing us. So kernel size is equal to 3 out of 3, or 3x3. And then we have padding to be the same, all caps. And we end with our random number generated key. We always make sure in JAX, you have to pass this RNG specifically. Sometimes you see it as RNG. That's how I like to do it. You could also see key, like the word key. Later on in this code, I use key for when we segment one of the random numbers. But yeah, and then we create a normalization layer called group norm. This is how many papers implemented, where we add 32 groups, and you have to make sure that the number of features is equal to the number of channels. And then remember, everything you have to pass the RNG through. That's the first convolutional layer. Does that part make sense? Don't worry about the normalization. And this should be out channels. Don't worry about the normalization bit. Worry mostly about this. This is a simple convolutional layer. And then we go on to the next one, because we got 2, right? We got conv 2. This is equal to another one of these. Except the input is out channels and the output is out channels. So we don't really change the features of the image. We just pass another convolutional layer through, and we add another normalization. Group norm. Literally the same thing. Let me copy this. And then remember the MLP that I explained, just so that our model learns what a specific time embedding means. And then when we call this, what we do is literally we pass self.conv x through self. The first convolutional layer, and we pass it through the first normalization layer. And then we add, let me scroll up real quick. You see how here we add our convolutional layer with a ReLU activation. In this case, we're going to use an activation called SILU, sigmoid learning unit, I believe. Swish. Nice. Sigmoid linear unit. Yes. That's what we're going to pass through. That's our first convolution. Then we work with the time embeddings, and then we pass another convolution, but this time with the context of the time embeddings. Same code. Does it make logical sense to this point, what we're doing? It's just too simple convolution. And I'll leave that up for a bit. Right after this, we work with our cross attention, and then we build our unit straight up. And so we're done with this bit.
Wait, isn't it norm two? So norm one.
Yes, right. Norm 2. We'll change that part and it should be, yeah, norm 2. And now we go here. This is where we start injecting our cross attention. Cross attention, the code is literally identical to how we did it in the transformer. If you guys remember, we could probably just copy and paste it, but we'd have to deal with some size things for the images. So here we have our cross attention layer. Remember, we have to define our number of heads. Whoops. Self dot number of heads is equal to number of heads. Self dot head dimension. Remember, this is that dk is equal to channels divided by number of heads. And we also have another normalization here. Also group norm. They like to use group norm a lot when working with diffusion models. So a number of groups is 32, and then we have the features equal to the channels. Same code and same group norm logic that we had in the previous steps. That's what we defined there, and then we define the attention matrices. So first we have the weight matrix for the query. And that's nnx.linear, channels, RNGs equals RNGs. And I'm gonna go up, this query belongs to the image because the image query attends to the key and the value. If you remember, let's say we're talking about the red car. When we're drawing that image, so let's say we have a specific pixel, that pixel is basically asking this sentence, what words here best describe me, so that I can make a change. This red would tell it a specific intensity of red for that specific pixel. And we do the same. So that's why we define our query weight matrix. And you see here, yeah, we implement the query matrix, and then we also implement the keys. And then the size of the keys is context dimension. Because remember, this belongs to the text. So the key belongs to the text. The key value, right? The value also belongs to the text. Thus, they have the same size. Makes sense, right? And then we have our output layer, or our output matrix. That's kind of just what we define at this step. And now in our call, here we perform this this cross attention. So remember, the X that we're passing through here is an image. And an image is, remember what we talked about is batch, height, width, and channel for color channels. This is what's equivalent to x.shape. And remember the attention residual. So here, let's just call a residual and make it equal to x. So the residual, if you see, when we pass the x and we do like the whole attention stuff here, what we output gets added to this residual. Think about it as updating the original embedding with the given context. And that's why we keep the residual. And here we want to flatten the dimensions so that we can perform the operations and the matrix operations between everything. So we're going to say H, that's just like our normalized X image, and we're going to rearrange it. We're going to make it flat, right? So we're going to also rearrange it, use this einsum notation, in which we take H. And what's the size of H? It's batch, height, width, and color channel, right? We talked about it just right now. And what we want to do is we want to multiply batch height with color channel. We want to multiply these so that our size is batch, whatever this goes to be, and channels. That's a three-dimensional vector, a three-dimensional tensor. So we do this in code like this. I think this notation is really like satisfying, because you just, and not flat. This notation is really satisfying, right? You literally see just the same way you'd write it out. You see the rearrangement of the dimensions. And then we calculate the Q, K, and the V. So Q is self dot WQ, and we pass H flat, right? Because H flat is our image. We multiply that by the weight matrix for query. And then key, remember the keys belong to the text. So what we pass through these matrices is the context. When we talk about context, we're literally talking about this sentence right here. And get that intuition that the query from the image side asks the text, yo, what should I be? That's basically the biggest, I guess, intuitive breakthrough you could have from this. The image is asking the text what it should be. So that's why it queries it. And the keys and the values give it some value for that. And now, here we're going to have a function to reshape these matrices. I don't know what to see. And this is another rearrangement, right? So we're going to return. The reason we're doing this rearrangement, remember, we're not doing it, we have multiple heads, so we want to do attention for each specific head, right? We do this for each matrix. So we have B and N heads D. This is the original size of it. We're considering that it's the batch. The N is like the size of the input N. And then we're considering that this last bit, which is the embedding dimension, is a multiplication of heads and the dimension per head. And what we want is to kind of split this apart so that we have a tensor per head that we're using for attention. In this case, we're using 8 heads. I think that's what we used in GPT-2. We might have used 12. But you probably remember this code bit by bit, where it's B head, and sorry, this is head, N and D. And what that means is that head is equal to self-dot number of heads. And we just do this for each value that we have from there, right? And do that. I'm not too familiar with that type of code, so I'm gonna just do it the way that I have it in my notes. And then this is the dot product attention function. This simple implementation, we know how to do this. We're back to the copying math. So first we're gonna define a scale. It's 1 over the square root of the number of, or the head dimension. And remember, the head dimension is this part right here, now that we divided it by the head. And then attention, we're going to do some einsum, some very, very satisfying einsum. So what we're doing in this step right here is that we're doing this query times the transpose of K. And so the size of query, we're going to call it BHID. That's the size of the query matrix. And then the size of the transposed other matrix is the size of the other matrix, I'm sorry, is BHJD. So this is the size of the query matrix, the dimensions of it. This is the dimensionality of the key matrix. And when you do, for example, I'm gonna start erasing stuff here. I don't think we need like this bit. When you do matrix multiplication, I'll show you exactly what's going on here. That was the worst matrix I've ever drawn. Let me remove. So we do matrix multiplication. You remember the height or the size of this has to be the same as the size of this. So in this case, what are we looking at? We're looking at I and D for this one right here, the query. And for the key, we're looking at J and D. We can't really multiply this, right? That's why we do the transpose of this. So this becomes D and length J, or number of columns J. Now we can multiply this with this, and our resulting matrix is number of rows is I, and then the number of columns is J. And that's why this resulting multiplication is now BHIJ. Does that make sense to that point? And we do this for the query and the key. So we got this part done. And remember, we already defined the scale. So that's where are we at? Right here. We multiply it by the scale that we defined up here. And then we just apply softmax on top of it. So attention is equal to softmax. And now our output, right, we still have to multiply it by this V. So we have now, we're going to do another einsum where we have BHIJ, right? This is the one that we got from here. We have BHIJ and we want to multiply it with something of size BHJD. Why is it BHJD? If you remember, we initialized the value matrix to be the same size as the key matrix. So it's literally the same thing, BHJD. And we multiply this to get BH, for the same exact reasons we get BHID. Let me make sure. And that's where we multiply our attention with our value. And then we just rearrange this so that we could shape it the same way as the rearrange. So we could put it back to the shape of what an image is. So BHND. Imagine this is like the BHID part. So BHND, and remember originally it's BH. This is our BHND. We're just turning head to H. We're going to turn it back to this size, BN HD. And we do that to out. We pass this through the out matrix. And then we just reshape this so that we make sure that we are passing an image, the same shape as an image, which an image is batch, height, width, color channel, or just channel in general. And here we just return our output. And remember, we have to add the residual that we added up here. This is our attention block here. So cross attention's done. The double convolutional layer is done. So now let's go straight into building our down block, which in this instance, our down block would be one of, one of these, and our up block would be one of these. So remember, a down block has a double convolutional layer that we defined up here, double conv, and we have our in channels, our out channels. We pass our time embedding dimension, and we define the RNGs. And then we have our attention, right? Each block has attention. Or I told you guys that the first layers weren't going to have attention, so I added this Boolean value here. So if that layer needs attention, then we add attention. If not, then we don't. But first, let's just initialize the attention variable at that step. It's cross attention. If use attention is true. Otherwise, we just don't have attention for that layer. And when we pass X, remember now this is where we pass this is what we pass into our neural network, right? We pass our image, our time embedding, and our context for that step. So X equals self dot our double convolutional layer, X given T. And then if we have self-attention, we do this X equals self-attention with the context. And now in the down block, remember, very important, we save the skip value. So skip is equal to whatever we have right now. And that is before we perform our max pool function. Max pool of X given a window shape of 2 by 2. And what is it? A stride of 2 by 2. This basically halves the size of our image. This is what we return. X, and remember, let's keep the skip intact. So what we did there is literally, boom, you see double convolutions, max pull down, and we keep the skip at this layer so that we can send it out to the other side whenever we do the up block. And that's our down block. For the up block, it's the opposite thing. So first we do the up sample. This up sample is using a convolutional transpose. This is just where we go from a smaller dimension to a higher dimension. Inputs are in channels and in channels with a kernel size of 2 by 2 and a stride of 2 by 2, as well as same padding, same. And always pass the random number that we have generated. And then look at the up block. It's the same function, right? We have a double convolution, and then we have, whatever we add, but we do have a double convolution there. Plus, we do have the attention. So it's same code here again. We have our double convolution, but one thing to watch out for, remember, we're sending out the skip channels. So we have the in channels plus the skip channels as our input. Our output is the out channels, and time embedding dimension as well as RNGs is equal to RNGs. And we just call back our attention again. Cross attention, which is what we built ourselves. Cross attention, out channels, context dimension. Then our RNGs is equal to RNGs if we want attention in that block. Otherwise, no. And then the code is simple. First, we up sample, and then we concatenate the skips. So we just get the skips, we pass them as a variable, right? And we add them. We literally just stick them to the end of our upsampled block at that point. X is equals -1. And there we do self or a double convolutional layer given our current time step and our image. And then as we did with the method above, we check if we have self-attention for this block. If we do, we apply cross-attention at that point. I keep saying self-attention, but cross-attention is a more correct term. And then we just return X. What code is this for? There's nothing there. And so that's our individual down down blocks, right? And up blocks. So now let's build our unit fully. So what do we have for our unit? I'm going to give you basically the parameters that I used for this implementation. So we initialize our unit. We start with 4 in channels. Why is that? It's because when we pass our image into the latent space, we have a 32 by 32 by 4. And we're keeping this color channel. In an image, it would be, in this case, 256 by 256 by 3. But since we're passing a latent space variable, here it's 32 by 32 by 4. And we also have the blocks of the out channels. We start with 128 dimensions to 256, 512, and 512. We have a time embedding dimension of 256. The context dimension of 768. Same number as the clip. Remember, we are using clip after all. And then attention levels. This is another list that we apply per block. Attention levels, the first level, like I said, we're not going to use attention in the first level, but then in the other 3 levels that we're going to have in our system, we are going to use attention. Here we'll put this keyword argument so that whenever we pass RNGs, you have to specifically define like, yo, let's use RNG. This part where I keep doing RNGs equals RNGs. We do that because everything that comes after this, we have to specify. And I think it just builds good practice of using RNGs and not forgetting to use it, because in JAX, you have to kind of use it at every point. So first, we're going to start with the time MLP. This will be a sequential block. Let me build it. Right. We're first going to go. You can kind of see this similar as our multi-layer perceptron that comes after attention in GPT. Just think about it as learning the higher level patterns when it comes to the time. So we pass it to a dimension that is 4 times bigger than the original dimension, and then we pass it back down for 1 step. And then remember, RNGs is equal to RNGs. That's our time multi-layer perceptron. And then we're going to work with our initial convolution. We're going to have an initial convolution. Let's define it here. Init conv is equal to just a convolutional layer where we pass the number of channels into out channels is the first block, right? And same thing, right? Kernel size is equal to 3 by 3. Padding is equal to same. Whoops, same. And then, as always, RNGs is equal to RNGs. And now let's build our unit encoder. The encoder is literally the part that just goes down. So we're going to create a list of our down blocks. So, right, we define. What did I do wrong here? Block out channels. So we have our down blocks. And our in channel is the output of the other out channel. So in channels is equal to the 0th index of block out channels. And now what we're going to want to do is that for I and our out channel in, let's enumerate our blocks. We are going to basically append to our down blocks a new down block. So we create a down block per step. Here we take as input the in channel, the output is the out channel. We take the time embedding dimension, our context dimension, right? We're just passing our variables through. We want to pass attention levels I. This is the use attention that we had. And then as always, RNGs is equal to RNGs. In this first layer, we're at layer 1, right? in channel, we're in layer 1, right? Or index 0, that is false. So we're not going to use attention for this portion. So we're done with that. And now our new in channel is equal to our current out channel. And then our channel overall is equal to our new in channel. That's just the encoder. Now we have the bottleneck, right? That's the bottom part that we have. Bottleneck. The unit bottleneck is self.bottleneck equal to, it's a double convolutional layer. You see it in the diagram as well. But we pass channel, we output channel, so we don't change the size. And then we also add attention to this part right here. So bottleneck attention is equal to cross attention. Channel context dim RNG is equal to RNGs. Cool. Now we gotta upsample it, right? So we literally do the reverse of this part. I hope you kind of see how it's logically simple. You're just building specific blocks and then you're stacking them on top of each other until you have the full network. So we have up blocks. We're going to create the reverse channels because obviously we're going back up, not down. And so we have list, reverse. We're going to reverse the block out channels. Those are the dimension sizes. And we're also going to reverse the attention. Same thing, list, reversed. Yeah, that was the name of the variable, attention. Whoops. And now for I in range, the length of reversed channels -1. We want to leave our final layer to ourselves the same way we kind of left the initial layer. We are just going to make the in channel is equal to the reverse channels at I. Same thing with the skip channel. Because remember, we have to pass the skip channel through. So we reverse it. This is also at step I. And then our out channel is equal to reverse channels at I+1. So our output is the next step in that. And here we do the same thing. We create a new up block and we append it to our up blocks. And so we put in our in channel, our skip channel, and our output channel, as well as our time dimension, our context dimension, and if we used attention or not, that is dependent on our attention list of booleans, and then RNGs equals RNGs. And then always make sure that the new channel is equal to the new current channel is equal to the output channel. And then we're going to make one final, like I said, we have a final up block layer. We create the up block, and now we have an input of channel, but our output is again block out channels 0. Or this is the skip. I'm sorry, this is the skip. And then we have the channel, then again, pass everything that we've been passing through up to this point. Context dimension, attention levels. Now we're back at the surface of our network. So we're using attention level at time 0, and then RNGs equals RNGs. And here we just do our final projections, where we kind of have another normalization here. This normalization is to make sure that our numbers stay in check, especially for back propagation. Very important. We don't want some what's it called? Like vanishing or exploding gradients. We've talked about those before. Time 0 and RNGs is equal to RNGs. And then we do the same thing for this final convolutional layer. I don't have to write it out. Yeah, I do. Conv equals next dot conv channel in channels kernel size equals 3 by 3. And same thing, padding remains the same, all caps. RNGs equals RNGs. Remember, we are taking in the image, the time, and the context. And I want to just make sure we have that clear, the time embedding. And I guess we'll just build each part now. We're going to see how our information flows from the beginning of the network to the end of the network. So we'll start with the time multi-layer perceptron, where we get T and we find the embedding of T. Given our time embedding. And then T equals self.time MLP.layers. So this is the first layer of it. If you remember, we had 2 layers. So here we throw it up into a dimension that is 4 times bigger than the original one. And we apply silu. So we apply an activation function, and then we literally bring it back down. And then we have our initial convolution, and that's just initial conv at x. And now we build, or we pass our information through our encoder. We want to make sure to keep track of our skips as we code this along. And so for block that we have in self.down blocks, remember that we built this. We want to make sure that we get the outputs. So x, t, and context. Remember, a down block outputs the downscaled image as well as the skip image. And what we do is just append the new skip into our skips list that we made up here. And then we do our bottleneck. So that's the very bottom, the deepest parts of our network. So self.bottleneck is x at time t, and then we also pass the attention at that part. And for the decoder, it's literally the opposite of encoding. So we still traverse through a list for block in self.up blocks. We pop a skip layer from our list, and x equals we pass that skip through the decoder. And then we do that for one final layer. So skip equals skips.pop, and x equals self.final. Our final up layer, it's x, skip, t, and context. And then we kind of do the final normalization at this point. We still do silu at x, and final convolution, and what we return is x. So that's our UNet architecture. We built this from scratch, this whole thing, right? That's what each part of that code did. If you're confused or if I went too fast, I'm recording this like always, so I'll post it on YouTube. But if you look at this code enough, you're going to see that it makes perfect logical sense. And now we go straight to our final model, right? We have to initialize our scheduler that we created at first. And that's the DDPM scheduler, where the number of time steps is equal to num time steps. And then we create our UNet architecture, which is a UNet. And now here we define like the specific variables for it. So in channels equals 4, block out channels is what we said, 128 by 256 by 512 by 512. Context dim, we just pass everything through there. And taking a little time to build that, but remember we pass our RNG. And here I am creating a NumPy array of size 164, 64, 4. If when we pass it through our unit, the last size should be the same size as the input. And let's see if that's true. Oh, wow. Well, norm to, I think that's because I forgot to, when you corrected me on that part, I probably forgot to, yeah, run it. So let's just run each step here. Should work. We should have the same output as the input. If it doesn't work at this step, well, at this point, I'm assuming it is. But remember, we have the final code to look at. So yeah, while that loads, no attribute final norm. Yeah, it's always some spelling mistake that's going to kill you. But it ran through the network, so we know that it works. Yeah. And here we just create some optimization steps for our actual training. And yeah, this is the part where we do the CFG. We're running a little tight on time. This lesson was a little more than I thought. This was a little too much code. But we're going to implement algorithm 1 of the paper. Let's see if yeah. I think this part's pretty important. So let's run through this really quick. This is the forward diffusion part, right? So we sample some normal noise, the size of the latent shape, and we get a time step that is random between 0 scheduler.num time steps. What we're doing at this point, or actually maybe I could leave you guys to implement this yourselves. We're exactly as it says here. We are implementing that in that same specific way, right? So we're getting the noise. Obviously, after we get our image, we get the noise and we get the time step. And after that, we pass it through, oh my God, noisy latents. Scheduler dot add noise. So we just add noise to this image, right? We have the latents, we have the noise, we have the time steps. Latents in your mind, always think of image. And then this is the CFG part. If you remember, we take the output with the classifier, then the output without the classifier. But I think let's kind of skip this part. This is just a dropout mask, like when we did with the attention, when we did with GPT-2. Again, all this code is complete in the final version. It's just a lot. I didn't think it would take that long, honestly, but yeah, let's skip this part. Let's go straight to our Mickey Mouse loss. Remember, all this complicated stuff kind of just boils down into a simple MSE function, if you remember that, which makes this really easy to train or really easy to lower the weight. So first we get the prediction given our noisy latents, our time steps, and our embeddings. At this point, we embedded classifier free guidance into some of the embeddings. And then our loss is literally the mean of the distance between the noise. And yeah, I think that's probably one of my favorite parts of this whole code base is that. And yeah, I mean, from here, it's pretty much the same stuff. We implement, I'll leave this to you guys. It's not that complicated at all. It's just following and understanding what the algorithm is telling us and re-implementing that in the paper or in the code base. That's what we do in the inference side of things. That's algorithm 2. And I'm not done training the model, or I had 50 epochs. I wanted to test out specifically on this UI that I made, but I think I'll just show you guys kind of some of the training steps. So as you can see here, these are some sample prompts that I'm injecting to an image every 10 epochs that we're training. So I want to track the progress of the image, right? A cat in the grass, a red car on the highway, and a sunset over the city. And so this is in the first, what is it? In the 10th epoch, this is our output. This is a cat in the grass. Doesn't look too much like anything, I wouldn't say, right? This is a red car on the highway. It's starting to form the red bits, right? And you can see that it's following the prompt to some capacity. And then this is a sunset over the city. We're matching the colors of what a sunset would look like, right? It's orange. And then we go to epoch 20. Let's go to, I believe this is epoch 20. This is the new cat in the grass. It's starting to kind of shape more the body of a cat, I guess. You see the grass still taking shape, but at least the colors are making sense at this point in training, right? 20 epochs in. Here is the red car. You see a little bit, I don't know. This is a little bit of the shape of the car. There is a gray floor, so it's on a highway or on some kind of road. There are mountains in the background, sort of. So we're starting to make more sense of our image. There is, I don't know what car that would end up being, like a Bronco or like a Jeep or something, kind of in the shape of it. And then this is a sunset in the city. You can see that the generator is starting to create buildings, and it's starting to, this would be kind of like a bridge, and it's starting to understand the concept of a city and such. And then this is the 30th epoch. A cat in the grass still remains very abstract. You can tell that it's getting good at the texture of grass. The cat part, not too much, not yet. That would be probably because of the fine details of a cat. It has a lot of the cat hairs, the face, right? These are small details that it still has to pick up on. It's getting the texture of the grass good, which is, good progress for epoch 30. Red car on the highway. I'd say that maybe in the shape, it remained the same, right? It didn't really learn the shape of a car too much better from epoch 20, but it's getting more fine details. You could kind of see, to me, this is kind of like the grill of a car in a way. There is, again, road and trees in the background. And that could look like, if it generates for a couple more epochs, it could look kind of like a forest a little bit in the background. And to me, this is the most impressive image that we've had output. This is epoch 30 for a sunset over the city. You can see here, it looks kind of like an impressionist painting, so you don't get too much details out of it. But I don't know, it looks pretty cool to me. You get definitely the vibe of a sunset or a sunrise. This is the sun itself, probably. And I don't know what part of a city we're in, but you see the buildings and things of that nature. So our model seems to be learning pretty well up to this point, 30 epochs with 120,000 images. Just for reference, Stable Diffusion was trained on 5 billion images. So we always have that little lack of data set overhead on top, right? But yeah, our architecture did this from scratch. We built it ourselves. So I think that's really cool. And I'll make sure to make this into a repository and give like some suggestions for resume points. I'll try to do that by Friday, especially as a cool end to the guild this semester. But